a university group project assignment in C++ Bear.
Right, so this isn't just dry theory. This assignment is all about getting students to actually build something.
Applying these OOP ideas in, like a real-world context, it's a great way to see why they matter, not just what they are.
Absolutely. So for you, the learner, our mission today is pretty clear. Pull out the most valuable, most insightful bits about OOP from this assignment.
Whether you code every day or you're just, curious about how software gets made.
We'll break it down, make it accessible, maybe spark a few aha moments along the way. It's always fascinating seeing abstract concepts turn into actual software.
It really is. And this assignment, it really pushes that connection right from the start.
Okay, let's get into it then. What was the main goal? What were these students actually trying to achieve?
Well, the core objective was twofold, really. Design and implement a real application using C++ and focusing squarely on OOP principles.
So not just code that runs, but code that demonstrates they actually understand these OOP concepts.
Exactly. It had to show they got the ideas and could use them properly in a working program.
And which OOP concepts were highlighted? What were the key ones?
The assignment laid out the big ones: encapsulation, inheritance, polymorphism, abstraction, and composition.
Okay.
And also, crucially for making something useful, file handling, saving, and loading data.
Right, those terms pop up a lot. Why are these specific ideas considered so fundamental, so important in software development?
Well, because they offer really solid structure for tackling complexity. Think about encapsulation.
Yeah.
It's like creating little protective bubbles around your data and the code that works on it. It stops things from getting messed up accidentally, makes code safer, more predictable.
Okay, so like data hiding.
Exactly. Data hiding is a big part of it. Then you have inheritance. It's about creating is-a relationships. Yeah, like a savings account is a type of bank account. It lets you reuse code, sure. But more importantly, it builds a logical structure. Makes things easier to extend later.
Got it.
Polymorphism. That one sounds complicated, but it's about flexibility. Writing code that can handle different types of objects in a similar way.
Ah, okay.
Abstraction helps you manage complexity by hiding unnecessary details. Focus on the essentials.
Like a simple interface for a complex system.
Precisely. And composition lets you build complex things out of simpler, often reusable parts. And file handling, well, that's just essential if you want your application to remember anything.
Makes sense. They're not just buzzwords. They're like the toolkit for building robust, maintainable software.
That's a great way to put it. Software that lasts.
Now, to make this concrete, the assignment listed project ideas. What kind of applications were they suggesting?
Oh, it's a good mix, showing how versatile OOP is. Things like an online banking system,
Okay, classic example.
a library management system, restaurant order management, even an online food delivery system, or pet adoption management.
Wow, okay, that really covers a lot of ground. You can immediately start thinking how different concepts apply. Like, how would inheritance work in, say, that restaurant system?
Good question. You might have a base class like menu item, right? Then you could have derived classes like food item, drink item, maybe even dessert item. They're all menu items.
Okay.
But each has specific properties: ingredients for food, volume for drinks, maybe special prep instructions.
I see. So they share common things but have their own details.
Exactly. Or take encapsulation in the banking system. You absolutely need to protect account balances, transaction history.
Right. Keep it secure.
Encapsulation enforces that. You control access strictly through defined methods like deposit or withdrawal, instead of letting just any part of the program touch the balance directly. It's fundamental for security and data integrity.
That makes perfect sense. It's like having a bank teller manage the vault, not just leaving the door open.
Okay, let's zoom in more on these concepts. Encapsulation, the assignment mentioned data hiding and getter setters. Why the emphasis on getters and setters?
Well, the data hiding part, using private usually, locks the data away. Getters and setters are the controlled ways in. A getter lets you read the data, a setter lets you change it.
But why not just make it public?
Because setters allow you to add validation logic. Before you change a value, say an account balance, the setter method can check if the new value is valid. Is it positive? Does the withdrawal exceed the limit?
Ah, so it's a control point. You enforce rules.
Exactly. It protects the object's internal consistency. Getters also give you control. Maybe you format the data before returning it, or maybe some data shouldn't be readable at all. Okay, that clarifies it. What about inheritance? The assignment mentioned single, multi-level, hierarchical. Sounds like different family tree structures.
That's a good analogy. Single inheritance is simple. One child class inherits from one parent class.
Like dog inherits from animal?
Right. Multi-level is a chain. Poodle inherits from dog, which inherits from animal.
Gotcha.
Hierarchical is one parent, multiple children, dog, cat, bird, all inheriting from animal.
Okay. And the assignment said use it appropriately. What does that mean in practice?
It means making sure the ESA relationship is logical and makes sense for your design. Don't force inheritance where it doesn't fit just to reuse code. Sometimes composition that has a relationship is better. Misusing inheritance can lead to confusing and inflexible code.
Right. Choose the right tool for the job. Okay, next up. Polymorphism. Function overloading and virtual functions were mentioned. This feels a bit more technical.
It can seem that way. Polymorphism means many forms. It lets you treat objects of different classes in a uniform way, but they behave according to their specific type.
Like the speak example. Dog barks, cat meows.
Exactly. Function overloading is one kind. You have multiple functions with the same name, but different parameters. The compiler figures out which one to call based on the arguments you pass. It's decided before the program runs.
Okay, like different tools with the same name but different sizes.
Sort of, yeah. Virtual functions enable runtime polymorphism. This is often seen with inheritance. A base class can declare a function as virtual. Derived classes can then provide their own specific version, called overriding.
And the program decides which version to run while it's running.
Yes. Based on the actual type of the object you're dealing with at that moment, even if you're pointing to it with a more general base class pointer. It's incredibly powerful for flexibility. Think of a draw function for different shapes. A circle draws itself one way, a square another way, but you can just call draw on any shape object.
Ah, I see. That allows for really adaptable code. And abstraction. Using interfaces or abstract classes, how does that simplify things?
Abstraction is all about hiding the implementation details and showing only the essential features. Like your car's accelerator pedal, you just need to know press to go faster.
You don't need the specifics of the fuel injection system.
Exactly. In OOP, an abstract class is like a partial blueprint. It can define some common behavior, but also declare abstract methods without an implementation.
Like placeholders?
Kind of. Any concrete class inheriting from it must provide its own implementation for those abstract methods. An interface, often simulated in C++ with a class containing only pure virtual functions, is like a contract. It defines what methods a class must have, but nothing about how they work.
So it defines a capability like this thing is drawable or this thing is savable.
Precisely. It ensures consistency and lets you work with different classes that fulfill the same contract.
Makes sense. And quickly composition and aggregation. The Hazer relationships.
Right. Both mean an object contains other objects. Composition is the strong form.
Yeah.
The contained object is essential and doesn't exist independently, like a car has an engine. If the car is destroyed, the engine effectively is too in that context.
Okay.
Aggregation is weaker. The contained object can exist independently, like a department has professors. The professors still exist if the department closes.
Got it. Strong part of versus looser contains A. And the other things mentioned, static members, friend functions, file I/O, how do they fit in?
Static members belong to the class itself, not individual objects. Useful for things shared across all objects, like a counter.
Okay.
Friend functions are functions outside a class, granted special access to its private members. Used carefully, they can be helpful for certain operations between classes.
Like a specific helper function?
Sometimes, yeah. And file I/O input-output is just fundamental for persistence. Saving data to text or binary files so the application remembers things between runs, absolutely vital for almost any real application.
Couldn't agree more. An app that forgets everything isn't very useful. Okay, so that covers the structure. What about what the apps actually needed to do? The functional requirements.
Yeah, this is where it becomes a real application. They needed CRUD operations.
CRUD.
Create, read, update, delete. Basically, managing records, adding new ones, viewing them, changing them, removing them. Standard stuff for data management.
Right, like managing library books or bank accounts.
Exactly. Plus search and filter capabilities so users can find specific information easily. They also needed to generate reports or summaries.
Useful for getting an overview.
Definitely. And very importantly, input validation. Making sure user input is sensible and doesn't break the program.
Crucial. Nothing worse than an app crashing because you typed your name where it expected a number.
You got it. And finally, a simple authentication system, usually distinguishing between an admin with full control and a regular user with limited permissions.
Adds a layer of realism and control. It sounds like they were building genuinely functional mini-systems. And explaining all this required detailed reports, you mentioned.
Yes, documentation was key. Reflects real-world practice. They needed a project overview, list of features, descriptions of their classes.
And that UML diagram you mentioned.
Yes, the Unified Modeling Language Class Diagram. It's a visual map of the classes and their relationships, inheritance, composition, etc. Invaluable for understanding the system architecture.
Like a blueprint for the software.
Exactly. They also needed code snippets with explanations, sample runs showing input and output, instructions on how to compile and run it.
Making it easy for someone else to understand and use.
Right. And details on file structure, who did what in the group, very important for collaboration, and even links to their GitHub and LinkedIn profiles.
Wow. Connecting it to their professional presence, too. That's thorough. How was it all evaluated? What carried the most weight?
Well, the two biggest chunks, 20% each, were application functionality. Does it actually work? And use of OOP concepts. Did they apply the principles correctly?
Makes sense. Those are the core goals.
Then code structure and logic was 15%. So clean, well-organized code mattered. After that came file handling, the user interface quality, the documentation, the UML diagram, report quality, and collaboration.
So a well-rounded assessment looking at the code, the design, the functionality, and the explanation. Any warnings or important notes?
Oh, yeah. Big emphasis on active contribution from everyone. And a strict zero-tolerance policy on plagiarism. Copied code meant 0 marks.
Ouch. Good incentive to do your own work.
Definitely. Plus, they mentioned individual vivas, short oral exams, to check each student's understanding.
Making sure everyone actually learned it.
Yep. And a little carrot. Exceptional projects might get showcased by the department.
Nice. Okay, well, this has been a fantastic deep dive into this assignment and OOP through its lens. What are the key takeaways for listeners?
I think the main thing is that OP isn't just academic theory. It's a practical approach to organizing software around objects, things that have data and can perform actions.
Combining data and behavior.
Exactly. And principles like encapsulation, inheritance, polymorphism, they're tools to build software that's modular, reusable, and easier to manage as it grows or changes. This assignment really shows that process in action.
Moving from just knowing the definitions to actually using them to solve problems and build something tangible.
Precisely. It's about that way of thinking, organizing complexity.
It really is a different way to structure your thoughts around building something complex.
Which actually leads to a final thought, maybe something for you, the learner, to consider.
Oh.
How might these core OOP ideas, identifying key entities or concepts, defining their properties and behaviors, thinking about their relationships like is or has a, how might that way of thinking apply outside of coding? Could it help organize complex tasks, systems, or even responsibilities in your own work or life?
Thinking about your life or work in terms of objects, their attributes, and interactions, that is a provocative thought. Definitely something to mull over.
Food for thought.
Indeed. Well, thank you for guiding us through this deep dive. It's been really illuminating.
My pleasure.
We'll be back soon with another exploration. Let us know what materials you'd like us to tackle next time.